going to be talking about intermolecular forces here. And intermolecular forces, we're going to define those as being the forces that are between molecules. So we're going to contrast that with what we talked about in bonding. And so those are those covalent bonds, which are the forces within molecules, or ionic bonds, the forces between atoms, or sorry, between ions. And so, if we have something like, let's say, water, where you have an H, an O, and an H like this, they are covalently bonded together. And so we would say that that connection between the H and the O is our covalent bond that's right here. And so that is not an intermolecular force. That is a bond, a chemical bond here. Similarly, if we had something like an NaCl, where basically the sodium atom gives its electron to the chlorine, creating a sodium cation and a chlorine anion. And so those two are going to be attached together because those are ions. That would be an ionic bond. But if we had a situation where we are looking at, let's say, two different water molecules, this one right here that we have, that's the OH like this, and we have another water molecule that comes out like this, and we're talking about the connections from one water molecule to the other water molecule, and so those are intermolecular forces. Now, these intermolecular forces are due to the same type of electrostatic forces, and remember, electrostatic means attractions between positive and negative charges as chemical bonds. And so they have the same cause behind them, but they're much, much weaker, generally less than 15% as strong as you would see from a covalent bond. And so that's when we talked about that when we talked about covalent bonds, is that unlike ionic, where we have these crystal lattices where we go like an Na goes to, it's not an Na, goes to another Cl, and they just connect one to another like this. And so they keep making the Cl's around here, and they all connect up like that. We said that covalently bonded substances form molecules, individual pieces that are very, very strongly bonded within, but very, very weakly bonded without. And those weak bonds are these intermolecular forces. Not very strong, but they're still responsible for a lot of characteristics of covalently bonded substances. And so it's the reason why that covalent things form liquids and solids. That should be not liquids and gases, that should be liquids and solids. So the reason why that covalent compounds form liquids and solids, it determines their boiling and freezing points, determines their viscosity, how thick the liquid flows, their evaporation rate, the energy that's needed to change phase. And so if it weren't for the intermolecular forces, then we would expect that pretty much every single covalently bonded compound would be a gas, and that's clearly not true. We are primarily made of covalently bonded compounds, and we're very clearly mostly solid, well, with liquid inside of us for the most part, as human beings. But these are these intermolecular forces, not as strong as the chemical bonds, but still very, very critical in understanding how these substances work. So we're going to look at four major types of intermolecular forces. And just for the purpose of this, we're going to abbreviate that as IMF. It's not sort of an official abbreviation. I'm just using it just to save space here. So the four types we're going to look at are ion-dipole forces. We're going to look at hydrogen bonding, dipole-dipole forces, and something called London dispersion forces. Sometimes they're called London forces. Sometimes they're called dispersion forces. Sometimes we put it all together and call them London dispersion forces. And of these types, the very last three, hydrogen bonding, dipole-dipole forces, and London dispersion forces, are collectively called van der Waals forces. The reason why, well, it's named after a guy, van der Waals, but the reason why we separate them out is that these three are all just neutral molecules. They cover those types of things, versus the ion-dipole forces, where one of the parts is an ion. And so not all of it's neutral. We do have a charged particle that's in there. But van der Waals forces are ones where all the particles are neutral. Okay, so let's look first at that non-van der Waals force, the ion-dipole force. And so ion-dipole forces are the intermolecular forces between ions and dipoles. Sort of makes sense here. So these forces typically exist between solutions of ionic compounds and polar covalent compounds. So remember, we said that like dissolves like in the bonding unit here, is that the things that are ionic tend to dissolve in polar covalent compounds. Well, the reason why is due to these ion-dipole forces. What happens is, so let's say we have this picture up here. I have an anion, and so that's right up here. And so you can see that it's an anion because it has this nice little negative charge that's right there. And I have a polar molecule, which has its little delta plus on one side and its delta minus on the other. So because of the fact it's polar, it has clearly a little more electronegative element somewhere over in here. It's drawing those electrons over to this side, leaving this side as negative and this side as positive. Well, what's going to happen? This little positive end that's right here is going to attract to the negative anion. That's going to pull those together. And so that is a force that attracts those two particles together. The negative ion, in this case, to the polar molecule, the positive end of the polar molecule. In our other case down here, we see we have a cation, a positive molecule, or positive ion, which is going to then attract to the negative end of the dipole that's this polar molecule. And so this is basically how ion-dipole forces work. Basically, the rule is that they are stronger with larger charge ions. And so like if this anion is a -1, it's not going to be as strong as if that anion was a -2 right here. Similarly, as if this polar molecule here, the greater the polarity, that is, the greater the difference in electronegativity between the two ends right here, the stronger we're going to see the ion-dipole forces. And so that's going to determine sort of how well certain substances dissolve, ionic substances dissolve when they're in polar covalent compounds. So let's suppose that we've got these situations. Each of the following is dissolved in ammonia, NH3, which have the strongest intermolecular forces. So NaCl dissolved in NH3. Well, first thing we have to see is, will these even dissolve? So NaCl, we want to see, is it ionic or covalent? We look at our electronegativity values. We see that sodium is 0.93. And chlorine down here is 3.16. And since that value is greater than 2 for the difference in electronegativity, this will be ionic. And so this is going to break up, as we sort of said before, into an Na plus and a Cl minus based on just looking at the periodic table and seeing that sodium is going to want to give away 1 electron to have a full outer octet. And chlorine is going to want to gain 1 electron because it has 7 valence electrons currently. And so sodium will be +1, chlorine will be -1. Now NH3, we look at, that's ammonia is what the name of that guy is. So nitrogen has is 3.04 for its electronegativity. Hydrogen is 2.20. So definitely not a difference of 2, so it's not going to be ionic, but is it polar covalent? Now the difference in electronegativity has to be above 0.4, and this is definitely above 0.4. So ammonia, NH3, is going to be polar covalent. And so because of that, we know these will dissolve. Now, next thing we're going to look at is the question is, which has the strongest intermolecular forces? Well, we have our solvent, that's the NH3, the thing that's dissolving. We'll talk about that when we get to solutions. Is going to be the same in both cases. We have NH3 for both of these. And so that difference here between the 3.04 and the 2.20, which is a difference of a difference in electronegativity, we'll say it's delta En, the difference in electronegativity or change in electronegativity between these two is going to be 0.84. So it's the same for both of those. Now, for our sodium chloride, we don't really care about the difference here because we know the NaCl is going to break up into ions. Let's compare it with the MgO. Is that going to break up into ions? Well, magnesium is 1.31 for its electronegativity, and oxygen is 3.44 for its electronegativity, and so that's more than 2. And so we know both the NaCl and the MgO are going to both break up into ions, and so they're both ionic. They'll both dissolve here into this polar ammonia, NH3. But the question is, which one has the strongest intermolecular forces, specifically the strongest ion-dipole forces? Well, we said there were 2 factors that affected this. It was larger charge ions and more polar molecules. Well, the molecules have the same polarity. They both have that electronegativity difference of 0.84. But what about this MgO? What does it break up into? Well, magnesium, if we look at it, has 2 valence electrons. It's going to, since it's got a low electronegativity, it's going to want to get rid of those in this ionic bond. So it'll have, Mg then will have a charge of +2. And then oxygen has 6 valence electrons. It wants to get that full octet of 8. And so it's going to need to gain 2 because it's got the higher electronegativity. And so these are our 2 situations. So we have our NaCl, which is an Na plus and a Cl minus. And then the magnesium oxide here, which is a 2 plus and a 2 minus. Well, it said that the one that will have the stronger ion-dipole forces is going to be the one that has either the largest polarity, which is the same because they're both NH3 here, or the one that has the largest ionic charges. And +2 and -2 are larger charges than +1 and -1. And so we would then expect, the question is which one has the stronger intermolecular forces? It's going to be this MgO in the NH3. That's how we know it. So let's look at another situation here. NaCl is dissolved in the following substances, which has the strongest intermolecular forces. In this case, we have NaCl for all three of them. They're just dissolved in different things. They're dissolved in NH3, SO2, and SbCl3. And so let's figure this out. So we said the two factors were either the ionic charge on the ionic substance or the polarity of the polar molecule. These all have the same ionic substance out front, so that's not going to affect it. The only thing that's going to matter is going to be the polarity of these guys, if they even dissolve in the first place. So let's find out. So NH3, we already actually figured that one out, has an electronegativity difference of 0.84. And so we can compare that with the electronegativity difference on these other guys. So let's look at SO2. SO2 is 2.58 is sulfur, 2.58 for sulfur, and then oxygen has electronegativity of 3.44. And so we take those two guys right there. That's not ionic, okay, so it is polar, and it's also not going to be it's bigger than 0.4 difference in electronegativity, so it is polar. So we'll do 3.44 minus 2.58, gives us an electronegativity difference of 0.86. So delta En, electronegativity difference, is 0.86. That's our difference in those two. Not a whole lot of difference between those two guys. Let's take our last one, SbCl3. So antimony trichloride. And so we've got Sb, antimony, which has an electronegativity of 2.05. And chlorine with electronegativity of 3.16. And so with that, it's definitely not as big as 2 for the difference. It's not ionic, but it's also bigger than 0.4, so it's going to be polar for this. So we'll say 3.16 minus 2.05, which gives us a difference of 1.11. So the difference in electronegativity is going to be 1.11. And so based on this, our ion dipole forces should be strongest for the one that has the highest polarity. And the one with the highest polarity here is going to be that antimony trichloride, that SbCl3. And so that means this one right here is going to be our situation that has the strongest intermolecular forces that are ion dipole forces. So let's look at our first one of our van der Waals forces, dipole-dipole forces. Sometimes, just FYI, these are called Keesom forces. You'll see that name used for them sometimes. But dipole-dipole forces are the forces that exist between two polar molecules. We addressed this a little bit during our bonding. We said if you had two polar covalent molecules, they form dipoles, they stick together, it increases the boiling point, increases the freezing point. These are because of these intermolecular forces. And so these forces are due to attraction between the opposite partial charges on the dipole molecules. So let's say we have this picture that's up here. The red is going to indicate a partial positive charge. The light blue is a partial negative charge. And so you can sort of see that what's going to happen is that this partial positive over here is going to attract towards that partial negative. It's going to pull these two together. And so we have this nice little attraction between the two. And so in dipole-dipole forces, these partial positive charges basically one attracts the other one in here. So dipole-dipole forces are stronger with stronger dipoles. So with molecules that have larger differences in electronegativity, we'd expect to see stronger dipole-dipole forces. And so we'd have a stronger intermolecular force that's going to hold the substance together better than ones that have very, very weak dipoles. So let's take a look. Which of the following substances would you expect to have the greatest intermolecular forces, NH3 or H2O? Let's try this one first. So to figure out this, if we had a mixture of NH3 of ammonia, then we first have to figure out, is there going to be dipole forces in this anyway? To be dipole dipole forces in the NH3, NH3 has to be a polar molecule. So we're going to look at NH3. So NH3 right here, we're going to say the N is going to have, look at the electronegativity of 3.04. The H is going to have an electronegativity of 2.2. We actually sort of did this already. And so that means this has a difference of 0.84. So the electronegativity difference is going to be equal to 0.84. On the other hand, if we look at water, H2O, so for H2O we have an electronegativity for the H. We already said that. That was 2.2, right? And for the O, if I can sweep it in here, the O has an electronegativity of 3.44. And so for those guys right there is the difference between 2.2 and 3.44 gives an electronegativity difference of 1.24. Both of these are well within the polar covalent bond, so this is not, neither one of these are ionic, neither one of these are nonpolar. But of those two, which one is going to have the greatest forces? 1.24 is bigger than 0.84, so it's going to be the H2O. So we'd expect to see stronger intermolecular forces between water than we would between ammonia due to these dipole-dipole or Keesom forces. Let's try another one, BRF5 or SbCl3. So let's look at these two guys here. So to do that, we want to do the same thing. Let's compare the differences in electronegativities. That's going to let us figure out which one's more polar and figure out which one has the greater intermolecular forces. So BRF5, so Br, bromine, is 2.96 for its electronegativity. Fluorine is 3.98, which gives us, for this guy, an electronegativity difference of, let's see, what is that, 1.02. So 1.02 for that. For the antimony trichloride, heck, we already figured that out earlier. Let's go back and see if we can find it on here. Antimony trichloride, we said, was 1.11. We already got that because that was the antimony trichloride. So we'll just go ahead and write that out. So delta electronegativity is equal to 1.11. And so of those two, we say which one is the larger electronegativity difference? This guy right here. And so antimony trichloride is going to have a stronger intermolecular force than bromine pentafluoride right here. Let's try this next one, SO2Cl2 or BRF3. Ooh, this one's a little interesting because this first one, SO2Cl2, seems to have multiple parts to it. It's not just a single, it's not just two elements. So this right here is, and I'll tell you this just because we need to know this here. This is a fully covalently bonded compound. There's no polyatomic ion in here. This is not ionically bonded. But to figure this out, we are going to need to draw out the structural formula because we need to see what's attached to what to see where the electronegativity differences are. So in looking at how this works, we know a couple things. We know that chlorine is going to end up being, probably is most likely, because it has, of these, look at our electronegativities. So sulfur has an electronegativity of 2.58. Okay, oxygen has an electronegativity of 3.44. Like this. Chlorine has an electronegativity of 3.16. Well, oxygen and chlorine are going to have the higher electronegativities. They're probably going to be the ones that are going to pull the electrons in tighter, and so that means sulfur is going to be the one that's going to sort of not lose its electrons. It's going to sort of, but it's not going to be the ones closest to them. And so that would imply that sulfur is going to be the middle of this molecule. And so if we look at this, I'm going to draw out a structure here. We have sulfur is going to be in the middle. We have two oxygens that are going to be out here and two chlorines that are going to be out here. And so we look at sulfur, and if you look at the oxidation numbers on sulfur, you'll see that if sulfur is going to have to give this up, sulfur has oxidation numbers of +4 and +6. And so in this case, it's going to be sulfur +6. Which makes sense because the fact that sulfur is going to give away, since it is the ones giving away its electrons, it's going to give away all of them because it's 6 valence electrons. Since here it's the least electronegative, it's going to be the one's going to have to give them because the other two guys, the oxygen and the chlorine, want those electrons much more than sulfur does. And so sulfur is going to give away 6 electrons, all 6 valence electrons, so it'll form 6 bonds. And so oxygen wants to form 2 bonds, chlorine wants to form 1 bond, so to draw this out, we have a double bond here, a double bond here, a single bond here, and a single bond here. Sulfur has 6, that's 1, 2, 3, 4, 5, 6. Each chlorine has 1, each oxygen has 2. Now, we know how they're hooked up. So now that we know how they're hooked up, we can figure out what our, which one of these is going to make the most polar bond. So we have S's and O's and S's and Cl's. Well, sulfur, we said, was 2.58. And so one set of bonds is going to be S2O, and that's the 3.44. And so that SO bond right here would be the 3.44 minus the 2.58. And so that bond right there, and the same is true for this bond that's right here, is going to have an electronegativity difference of 0.86. 0.86 right there. On the other hand, our other bond is a sulfur-chlorine bond. The sulfur-chlorine bond will be the difference between our sulfur right here and our chlorine, which is the 3.16 is our chlorine. So we take the difference between those two, 3.16 and 2.58. We get an electronegativity difference of 0.58. So equals 0.58. So we can very quickly look at those two, and we can establish that the 0.86 is our larger one. So since we're looking for the greatest intermolecular forces, that's going to be the one we're going to compare, and we're comparing this with the BRF3, the bromine trifluoride. Well, it's still bromine and fluorine here, and we already figured out that had an electronegativity difference of 1.02. And so since the 1.02 for the BRF3 right here is a bigger electronegativity difference than the largest of the two, the most polar set of bonds, which are these ones right here, in this guy, then we'd say the BRF3 is going to be the one with the greater intermolecular forces. All right, let's try one that's a little different here. So on this next one, I've got two compounds, this guy here, this guy here. For this one, I don't give you the formulas, I give you the structural formulas. And so we'll do the same thing. We want to look at the individual bonds and see if we can figure out which one has the greatest electronegativity difference. So first one we have here is this sulfur-oxygen bond on this guy. We already figured one of those out. That was the sulfur-oxygen here. Same difference is going to be 0.86. So 0.86 right there. The next one is this bond down here. It's a sulfur-carbon bond. So sulfur, we said, is 2.58. Carbon is 2.55. Well, those are only 0.03 apart. That's not even a polar bond. And so for that one right there, we know that's not going to be it because it's a nonpolar covalent bond. Our next one here is down here. It shows the C and then the H's. The C is H3C. What that really means is that it's got three H's. They're coming out of the C like this. They're all bonded to it. Same thing is true over on this side. So let's look at that carbon-hydrogen bond. Well, hydrogen is 2.2. Carbon is 2.55. Take the difference for those electronegativities. It's 0.35. Also, not 0.4. It's not polar. And so the only polar bond we have in this molecule over here is going to be that oxygen-sulfur bond that's right here that has an electronegativity difference of 0.86. For our other one over here, once again, we have some very similar bonds. We have sulfur to oxygen, which we already figured out was the 0.86. So that's the 0.86 right here. Then we have, the next one is we have a sulfur-chlorine bond. We already figured out a sulfur-chlorine bond is going to be 0.58 right there. And the new one is the sulfur-fluorine bond. So we look at fluorine. Fluorine has electronegativity of 3.98. Sulfur, we said, was 2.58. We take the difference there. We get an electronegativity difference, delta En, of 1.4. Well, let's compare all the ones we have. We have a 1.4 for our sulfur-fluorine bond. We have a 0.58 for our sulfur-chlorine, a 0.86 for our sulfur-oxygen, a 0.86 for the sulfur-oxygen over here. The highest one is going to be this 1.4. And so the most polar bond between these two molecules is this sulfur-fluorine bond. And that means that we'd expect to see greater intermolecular forces in this substance than we would in this substance over here. So that's how you'd use dipole-dipole forces, even in complex molecules, to figure out which one is more attractive to each other and has the greater intermolecular forces.